First of all, of course, I would like to thank the organizers for having me invited to Korea. It's always a pleasure for me to be in Korea. So my talk is in some sense a continuation of Fabrizio's talk yesterday, and since he started with line configurations, I will start with rigidity. And I have to apologize to those people who have attended the talk at KAIST last week, so there will be some overlapping. So if I have a compact, complex manifold, so this is rather general, n is the dimension, a deformation, everybody knows, of x is, well, I just consider smooth deformations is a f from x to delta, and I have a point t0 where f is a smooth proper map, and delta is a connected analytic space. And the fiber over T0, I call this X T0 is isomorphic to X. So this is a deformation of X. And I want to talk about rigidity, and I have different concepts of different notions of rigidity. So let me first say I want to take the equivalence relation generated by x prime is a deformation of x. So if I have another fiber here, t, so here xt is a deformation of x. Okay? And I want to have the equivalence relation, so I want to have change, so chains of such deformations of each other. And I say, I denote this x is deformation equivalent to x prime. Okay? Now, the first definition of rigidity, I will call this global rigidity. So x is globally rigid if and only if x prime is deformation equivalent to x, then it follows x is isomorphic to x prime. I will call, and this is what I understand usually with rigidity, x is locally rigid, and I will drop this local later if and only if for each deformation f from x to delta T0 such that x T0 is x, there is an open subset such that xt is isomorphic to x for all t in U. And then I have infinitesimally rigid, so I call x is infinitesimally rigid if and only if the first cohomology group with values in vector fields theta x is 0. Okay? So why is this infinitesimally rigid? Because this is the tangent space of the base of the Kuranishi family of the semi-universal deformation of X. So, and Kuranishi theory says if X is infinitesimally rigid, then this implies locally rigid. And this because H1 of theta is the Zariski tangent space of the base of the semi-universal deformation. Okay, so if you look at curves, what are the rigid curves? So you know that curves of genus bigger or equal to 1, they have moduli, and P1, the projective line, is the only rigid curve. Okay? And what about surfaces? So first of all, a remark I should have also put maybe here is that we have that the dimension of the base of the semi-universal deformations, the dimension is bounded by from below, and it's 10 times chi of for surfaces, sorry, chi of s minus 2ks squared. So of course, if this is positive, then the surface will not be rigid. Okay, and then there is a, let me call it a theorem by Fabrizio and myself, which is essentially an observation when surfaces can be rigid. So if S is a smooth projective surface and is rigid, then there are two cases. Either S is minimal of general type, and if S is rigid, is locally rigid, then also globally rigid, because we have a moduli space. Or S is a del pezzo surface of degree bigger or equal to 5. In this case, S is infinitesimally rigid. So h1 of theta vanishes.
What happens if you take P2 and blow up 3 points on the line?
It's not a del pezzo.
It's not a del pezzo.
Yeah, and you can move it away, the 3 points, and then you can...
Oh, yeah, of course.
It shows it's not globally rigid. Yeah.
Okay? So this exactly, I mean, you see the point is they're always infinitesimally rigid, locally rigid, but they are globally rigid only if it's P2. So B is globally rigid if and only if S is the projective plane. And Alexeyev's example shows that if you take a del pezzo, you blow up 3 points on a line, you can deform 1 point away from the line, and this is not globally. You will get a del pezzo surface of degree 6. Sorry?
Pezzo, the forms were weak.
Yes. Degenerate, right. Okay. So the proof is using classification theory. It's essentially a corollary of the classification theory, and essentially, if you assume S to be rigid and assume it not to be minimal. So, and then you use the fact, if you blow down the -1 curves, the deformations of S correspond to the pair of the blow down surface with the point. And so you get immediately vector fields, and you get immediately that -k is bigger or equal to 0. So, and then you can, and then you see that the surface has to be ruled. And then you only have to exclude Kodaira dimension 0 and 1, and you can suppose it's minimal. So it's really just an application of classification of surfaces. Okay, so now, but what are the rigid surfaces of general type? What are the known examples up to now? So that's not so much if one really thinks about it. So probably the most famous are the ball quotients. So these are surfaces uniformized by the complex ball. So S is B2 divided out by gamma, where gamma is a torsion-free discrete co-compact subgroup of the automorphism group of the ball. Then a similar example is by-disk quotients. So ball quotients are automatically rigid, and by-disk quotient, so this means S is uniformized by a product of two one-dimensional disks or two upper half planes by a discrete co-compact free subgroup. And there are two cases. If gamma is irreducible, so this means each projection on PGL2R, on each possible projection of gamma has dense image. These are automatically rigid. by results of Mosto, Seo, Mock, Jost, and Yao. Okay. But they're also reducible by these quotients. And then S is a product of two curves divided out by a finite group. Their special surface is isogenous to a product such that Ci mod G is P1, the projective line, and branched in 3 points. And this action is free.
Zero.
Huh?
You should take G is 0. The index to some.
Yeah, I'm not. Yes. I don't want to explain. These are the so-called Bouville surfaces inspired by a construction of Bouville, and they have been studied quite extensively by group theorists in the last few years. Okay, then there is another example.
So examples are all infinitesimally rigid as well?
Okay, so ball quotients, they're infinitesimally rigid, and the Bouville surfaces, we didn't check, we don't know that. They are infinitesimally rigid. Okay. So, but this is a good question. I mean, of course, there can be rigid surfaces of general type which are not infinitesimally rigid.
Because
but it's
theta minus log 3 points is H1 equals 0.
okay. So I don't know any example of a rigid surface of general type which is not infinitesimally rigid. I mean, one of course expects that there are. I mean, you just take a -2, you should have a -2 curve which doesn't deform. But constructing such an example is not, it's not easy, I think. Okay. Yes. Then there is the example by Mosto and Seo. This is a surface which is a branched covering. Yeah. Of ball quotient. So the reason why they construct these examples is they are not ball quotients, and they have a metric, a Keller metric with negative curvature, and it was conjectured that these are only ball quotients. And then there are certain double Kodaira fibrations which were constructed by Fabrizio and Sönke-Rolenske. So,
how about a surface with a fibration over P1 with 3 similar fibers or 2 similar fibers? This may be rigid.
yeah, I mean that's what we in the end we will get also as an example, but yeah, could be. Mm-hmm. So.
Is there any product quotient example? So is there any product quotient surface?
This is, I mean, where you could check for not infinitesimally rigid rigid surfaces, but I mean you have to show that that they don't smooth or that they don't deform, and this happens pretty often. So I didn't check these examples, or at least the ones which I checked didn't work out. Okay, so let me make a remark So the cases 1 to 4, they are projective classifying spaces. Which means, by definition, the universal covering is contractible. This is the first remark, and the second remark is actually most of these examples fulfill a much stronger rigidity condition. So 1, 2, and 4 are what we call strongly rigid, which essentially means that the topology already imposes rigidity. And precisely, I mean with this, if S prime is orientedly homotopically equivalent to S, then this implies that S prime is isomorphic to S, or S prime, the conjugate, complex conjugate surface, is isomorphic to S. So the moduli space consists of 1 point or of 2 points. Okay? Now, of course, if you have this rather short list, it's a natural question to ask, find more rigid surfaces. Well, it's not a question, it's how to say. Yeah, one should do this. And then, of course, you can ask, are there also projective classifying spaces, or are there rigid surfaces which are not projective classifying spaces? So in 3, it is a covering of the disk, right? But it's not a ball. And in 4, I forgot, it's probably it's homeomorphic to a bounded domain. Okay? So.
But it's a bounded domain with bad boundary.
Okay, so now let me come to the Hirzebruch-Kummer coverings that Fabrizio already mentioned yesterday. So what Hirzebruch did, he took line configurations in P2. Let's say it's given by a linear form, and you have k lines, and then you take essentially you take the nth root of each line. So the Hirzebruch-Kummer covering of exponent n S, it has functions. So birationally, this is given by the function field C x y, and then you take the nth root of Lj over Li, L1. Okay, this is a Galois covering of
So the nth root should go a little bit to the right.
of a blown up P2 with Galois group. C mod n to the k minus 1, where k is the number of lines. And what Hirzebruch did is he investigated line configurations and found conditions in order that this Hirzebruch covering is a Ball quotient, so that k squared is equal to 3c2. c1 squared is equal to 3c2. And this is all in actually there's a lot more in this book by Bartels, Hirzebruch, Höfer. So they give conditions on L implying, on the Li implying C1 squared is equal to 3C2 for S. And they actually gave 3 examples of Ball quotients in this way. So n is equal to 5, and you have the complete quadrangle. N is equal to 5, and the dual Hesse configuration, and n equal to 3, and the Hesse configuration, which was explained yesterday. So now, for the other n.
So I'm sorry, but you said you used the word configuration with a specific meaning, that the same number of lines for each.
No. I'm sorry. For me, a line configuration is just the number of lines.
So Hirzebruch
uses
makes the distinction. Hirzebruch calls that an arrangement.
No, he calls it a. Yeah, he's used. No. Actually, he's calling them configurations. I mean, in the German book, they are called configurations, and he explains that it means it in a wider sense than the classical geometrical configurations.
Yeah, that's fine.
So, okay. Okay, so a natural question here now is, so they're not, I mean, we have all these coverings for any exponent n, and for n bigger or equal to 3, they're of general type. And the question is, a natural question is, are they rigid for other n, or for the other n? Okay? Now, so the theorem that we proved is the following. The Hirzebruch-Kummer covering branched of exponent and branched on a complete quadrangle is infinitesimally rigid for n bigger or equal to 4. For n equal to 3, h1 of theta s is different from 0. So actually, the interest from this came also from, so Fabrizio mentioned yesterday the Catanese-Detweiler surfaces. So the corollary here is that the Catanese-Detweiler surfaces are also rigid. So what I don't want to give the exact construction, but there are étale quotients of these Hirzebruch-Kummer coverings, and there are coverings of P2 branched in these configurations, but the group is Z mod n squared. Okay, and why is this? Because if I have S prime, an étale, finite étale morphism, and S is rigid, then also S prime is rigid. The converse is wrong. So if S prime were not rigid, this is just a condition of a subgroup of the fundamental group. This would also hold for the deformation, and then you get a family also above. Okay. So now let me come to the second part, which is more about line configuration. So I want to say about the proof. And why I believe it works more in general. In fact, there is a joint project with Roberto Pignatelli where we believe we can prove the same for the Hesse configuration. But
What is an example, something with S prime rigid and S not rigid?
Yeah, take a Bouville surface. It's rigid, but the product of two curves is not rigid. Okay, so let me, in general, so we have to calculate H1 of theta for this branched covering. So I have L1, LK lines in P2, and I have M points, and these are only the points where at least 3 lines pass, the singular points of multiplicity bigger or equal to 3 of the configuration. So then I blow up P2 in this M points, and I have Pi, and over Pi I have EI. Now, how is the Hirzebruch? I need not only the birational information on the Hirzebruch-Kummer covering, but I need more. And by the generalization of Grauert and Remmert of Riemann's existence theorem, it's sufficient to give the unramified covering of y minus the branch locus. So let me call delta is L1 LK and E1 EM. And then the Hirzebruch-Kummer covering is given by a homomorphism of the fundamental group of the complement to my group G, but G is abelian, so it factorizes through the homology, first homology, to G. And this is C mod n to the k minus 1. So how is this given? To Li, or a small loop around Li, I associate EI, the ith basis vector for 1 up to k minus 1, and Lk I map to minus E1 plus Ek minus 1. So I could take C mod n to the k, and the hyperplane given by the sum of the coordinates is 0. Okay, and then what happens then? This determines everything. What is the image of EI? So if I have a point P, and then I have lines L1, L2, L3 or more passing, then EI is mapped to the sum of, let's say, phi of L1 plus phi of L2 plus phi of L3. Okay? So it's more complicated with the fundamental group. I have still some conjugates and the ordering matters, but here it's abelian. Okay, so now I claim that this morphism determines everything. So remark, and here, I mean, this was done by Rita Pardini, essentially on abelian coverings. So first of all, so if we have here pi from S to Y, this is our covering given here. And then we have, first of all, that pi lower star of OS, it's a direct sum. Psi is in a character, and the character sheaves. And then we have, we can also decompose the Serre dual of the tangent sheaf in isotypical in character parts, and this is nothing else than omega 1 y, and then I take logarithmic poles along d sigma where psi d sigma is different from n minus 1, and I have to tensor this with ky plus L psi. Okay? So what is this d sigma? D sigma is the component of delta having the cyclic group sigma as a stabilizer group. Okay?
Whose local monodrome is sigma.
Yes. Yeah, if you take then. Okay, and now how, so we have to calculate these character sheaves, and we have to then calculate the cohomology of these sheaves. So let me just give you a formula in the standard generators of the Picard group of P2 blown up in m points. So n times L psi, this is linearly equivalent to psi of phi of L1, no, not in the, sorry, let me just give you a formula in the branch locus, plus psi of phi of LK plus psi of phi of E1 plus okay. So okay, so now we have to calculate this the character sheaves for each n, and we have to calculate then the sigma, where psi d sigma is different to n minus 1, and then we have to calculate these cohomology groups. So you can imagine the bigger the configuration gets, the more complicated it gets. So let me give a lemma. So what we do is h1 of theta s is 0. I mean, this is the same as h1 of omega 1s tensor omega 2s, and this is 0 if and only if for each psi a character of g, so g is z mod n to the k minus 1, we have that h0 of omega 1 y log d sigma such that psi of sigma is different to n minus 1. Tensor ky plus L psi is equal to k plus L psi squared minus m minus 1 plus the sum over all sigma psi of sigma is different from n minus 1, 1 plus d sigma ky plus L psi. Okay? So why this formula? Because this is just the Euler-Poincaré characteristic of this sheaf. And we know that, so this is chi, so this is h0 minus h1 plus h2, and h2 is 0 because we have no global vector fields. Okay? Now, so how do we calculate? So we have the following situation. We have Y is P2 blown up in M points. And then we have rational curves on them. So let's say D1, R, smooth rational curves, and they have global normal crossings. Okay? And what we have to do is we have to calculate H0 of a sheaf omega 1 y log D1 log dr tensor with some, let's say, D. Okay? D. Of some divisor, which then in our case will be K plus L psi. So let me just do the first case. What is if D is equal to 0? Then there is an old lemma proved by Fabrizio. So you have an exact sequence, omega 1 y, omega 1 y, d1 to dr, and then you have the residues. Sorry, log, I'm missing here. Okay? Huh?
What is D?
D? D is, here that's just a divisor. I mean, I'm not, and here I just said D is 0. But these are normal, I mean, these are just, okay. So, okay, so then,
the lemma is not finished.
no. Then let me say the connecting homomorphism from direct sum H0 ODI is in H1 omega 1. So this is just given by the Chern classes, the first Chern class. Okay, and H0 of is just the kernel delta. So now what does this imply? If you go further in the exact sequence, then there's H1 of this. So if this, and then there is H1 of this, which is 0. So if this map is surjective, H1 is 0. So this implies that H1 of F is 0 if and only if the rank of D1 dr is maximal, m plus 1. So they generate the Pika group. Okay? So what does...
Why H1? Why H1 and not H0? And then
because H0 is not 0. If this map is surjective, then the next one is injective. And so H1 is inside H1 of ODI, and this is 0.
you forgot the twist.
Sorry?
You forgot the twist.
I didn't put any twist. I just put d equal to 0. Okay? So why is this important? Because the vanishing of H1 corresponds to a condition of the rank of these branch divisors in the Picard group.
Like this holds in general or just for...
No, this... What do you mean?
This,
This holds in general. This corresponds a rank condition on D1, dr. Okay, so and essentially we calculate the differential. We just verify this lemma for all characters, reducing it to this case.
So you could write instead of m plus 1, you could say h1 of omega 1.
Yeah. Yes. So, just to give an example, so in general, so K plus L psi will be of the form something like D1 plus D L minus D L plus 1 minus D mu. Okay? And we reduce this step by step to this case. For example, so apply or reduce to the above as, for example, the following lemma. Assume that f is omega 1 y log d1 d mu and d mu plus 1 plus d r. Okay? Let's suppose that this is effective and the sum of branch lines, branch divisors. So if these two conditions hold, di multiplied with the sum nu equal to 1 up to r, nu is different from I, d nu is bigger or equal to minus di squared plus 1. And if rank of d1 d mu is m plus 1, then h1 of f is 0. Okay? So it doesn't really matter what this condition is. What I want to say is I can encode, I can give a sufficient condition for the vanishing of these differential forms of H1 in the intersection behavior of the DIs of my line configuration, blown up also the exceptional divisors, and in the rank of this one. Okay? So what does this show? First of all, this shows that we can do a lot of the checking by computer. Once we have classified all the possible K plus L psi. Well, we did this for the first case, and I mean, this is what I'm telling you, we can apply it in a more general setting. So what you have to do still is to classify the K plus L psi. And it's not clear, I mean, you have to do this for all n, right? But still, there is just a finitely many possibilities, which only depends on the configuration. So this is a remark. If you have a character, any character, psi of G star, then L psi is of the form f of psi L minus lambda sum of lambda I psi ei. So L is the pullback of a line and ei are the exceptional divisors, and we know that f of psi is bounded by the number of lines minus 1, and lambda I is between 0 and the multiplicity of pi minus 1. So there are only finitely many possibilities. Of course, there are still far too many, and for this you have to use the symmetries of the configuration. And you still have to get hold. I mean, of course, you can ask always the computer to compute this, but if the configurations get big, this is not so easy. So let me just show you in the case of the complete quadrangle, where you use the S5 symmetry. So what we can show is the following. If you have so if you have so there are 10, the branch locus consists of 10 divisors, right? Let me just call them D1 up to D10, because I'm now not really explaining the geometry and the symmetry. So what we can show is the rank of, well, no, I mean, so what I want to say is if I take 7 of them, so I should not have so the rank of 7 bigger or equal to 7, it's always maximal. Okay? So if I take at least 7 of these, the rank is always maximal. So it's m plus 1, it's 5. So they always generate pick, and 6 of them have rank less than 5 if and only if they have rank equal to 4 And so we have on this Del Pezzo surface, we have 5 pencils. So, and if there are the 3 singular fibers of one of the pencils. So what are the pencils? L minus pi. So the lines passing through one of these points. So this is a pencil and it has exactly 3 singular fibers. And then there is the 5th pencil is the conics passing through. Okay. Now, still I still have to handle this log d sigma, where psi d sigma is different to n, and this is the following proposition. So the rank of d sigma with psi d sigma is different from n minus 1. This is less than 5 only in one single case, if they are d sigma psi d sigma is different from n minus 1 is equal exactly this configuration. So for example, you take blow up a point, E is this central one, and then the 3 lines through it. This is the only case. Otherwise, they always have rank 5. And the philosophy is if they have rank 5, then we can prove the vanishing of H1, as I showed before. So let me finish with a question. What is would be interesting to know is if you take rigid line configurations and you take abelian coverings branched over rigid line configurations, are they rigid at least eventually? Okay. So thank you.